Yeah, we have seen so far the important mechanical quantities, measurement of mechanical quantities like displacement, velocity, acceleration, force and torque. From now onwards, we are going to see some of the process variables, measurement of process variables like temperature, flow, pressure, like that. So, to start with, we are now seeing the temperature measurement. Now, the temperature is one of the 4 fundamental quantities along with length, time and mass and temperature. So, the standard for the definition for temperature is it indicates the kinetic energy of atom or molecule of a body. That is the that kinetic energy decides the temperature. So, any standard for the temperature should be able to measure the kinetic energy. So, such a method we do not have. So, the standard for the temperature is obtained from the fixed points. Fixed points standard is obtained from fixed points of 6 elements. They are mentioned in any clock table. For example, steam point 100 degree centigrade, and ice point 0 degree centigrade, and the melting point of gold, melting point of silver, melting point of sulfur. So, some of these are the such 6 points are there. So, based on that any instrument is calibrated. So, standard for temperature is the fixed points as defined in any clock table. One can refer the clock table. Now, what is importance of temperature? Temperature is a very important quantity in the sense it decides the state of any body, an inert body, an inert matter. So, the inert matter has got the solid state, and inert matter can have 3 states: solid, liquid or vapor, and all these 3 states are decided by the temperature of the that matter. And not only the temperature affects the any non-living body, for all the living body, the health of any living body is decided by the temperature. So, that means and also in many industries we find for manufacture of some material or say baby powder, and you have to maintain the product at the different stages of the manufacturing at different temperatures. Not only at different temperature for constant durations, also a temperature cycle. First half an hour one temperature, next second half an hour another temperature, like that temperature cycle. So, these have to be maintained properly so that we get the correct product as the output. Otherwise, instead of powder you may get a solid at the end. So, the temperature measurement is very important in all process industries and chemical industries. At various points temperature is measured and they are monitored and they are constantly watched by the operator, and the temperature is signal is taken to the control room and it is displayed. Hence, you find such an important parameter, measurement of such an important parameter, we have got many literatures. Even temperature measurement alone we have got books. But here we are going to see the important aspects of temperature measurements as a completion of the material for these mechanical measurements. Now, for the purpose of measurement of temperature, we use the effect of temperature on the bodies. It changes the physical dimensions or volume of the body, and electrical properties of the bodies or elements are changed when temperature is changed, and radiating capability of a body or matter is again a function of temperature. By using these properties of matter or material, we are able to measure temperature. First and foremost, one is say solid. Solid expansion of solid we are using in the form of bimetal strips. Bimetal strips. They are often still they are used in many of the refrigerators, where you find two strips, two flat strips. One is made up of inward, other is made up of say copper or brass. This is a brass brass tip. Both of them are fixed together, and then it is fixed at one end. This is a brass. See, invar is a material. It's a nickel steel alloy having a temperature coefficient of 1.7 into 10 to the power of minus 6, whereas brass has got 2.2 into 10 to the power of minus 5. You find more or less brass has got 10 times the expansion coefficient as invar. So you find when the temperature increase, naturally brass will have more length expansion than invar. So you will find when the temperature increase, it bends like this. It bends like this. It bends like this. So you find that is higher length. Higher length will have the outer of the curve bending. And now suppose if you have a switch point, something like that, then you will find it may contact. This may be a power on the power line. So when the temperature increase, it touches the point, contact point. So power is carried to the compressor of a fridge. So when the temperature comes down, then it becomes flat and the temperature is cut out. So it is on-off control. Mainly they are used in on-off control, such bimetallic strips. That is what is made use of. The expansion of matter, expansion of solid is made use of in measuring the temperature and controlling the measurement. Does not mean always exhibiting the value. Here it is measured, and measurement is done by bending. When it measuring means it bends this way or the other way, and that is being made use of for control purposes. It is called either on or off. It will be in two positions, two position control. That is expansion of solid. And now expansion of liquid, we are using in the mercury in glass thermometer. Mercury in glass thermometer. So we have that is well known. We have a capillary in a glass material. It may be going up to here. So this is a glass column, and at the bottom we have the bulb. So you find the mercury is rising in the capillary. So mercury is kept here. So it is a container, a small bulb, and when the whole thing is immersed in any bath, then you find the mercury in this bulb expands and rises over the column, capillary column, and this is being calibrated in terms of say 30 degree. This may be 100 degree centigrade. So it is being calibrated. This calibration is done by using one of the one or two of the fixed points. So ice point is 0 degree centigrade. So once you put ice and then mark that wherever it stands at 0, and boil a water and then place it this one, and where it stops, then you call it as 100 degree, and divide equally the gap between 0 and 100 into equal parts. That's how the thermometers are measured, are being calibrated by using the fixed points. So here what we are using, the expansion of the liquid is made use of in the liquid in mercury in glass thermometer. And the vapor, that is the physical dimension of the first principle is the temperature affects the matter and changing the dimensions. So that is the property what you are making use of in these instruments. So bimetallic strip, mercury in glass thermometer, and third we have got vapor pressure thermometer. Here we find it's a bulb. This is a bulb which is immersed in the body, or it is put in the furnace where we want to measure the temperature, and the free surface of the volatile liquid, the temperature at the free surface, this is the free surface of the volatile liquid, and that decides the vapor pressure. So you just immerse it up to this level, and you find the free surface evaporation of the free surface builds enough pressure depending upon the temperature. That pressure build-up is a function of temperature of the surroundings. So you find the same pressure is transmitted through this liquid, and this it goes to a Bourdon gauge. It's a pressure gauge. So it measures the pressure of the vapor just above the volatile liquid, and the whole tubing, everything is filled up with the non-volatile liquid. This is construction. So the pressure reading is now calibrated in terms of temperature. So this is the principle of a vapor pressure thermometer. These are often used in automobiles and cars, where the radiator water temperature is measured by a bulb like this vapor pressure thermometer, and the meter is put in as one of the dashboard instruments for the driver to see whether the temperature of the radiator water is increased. If it has increased, that means the water quantity is reduced, then he is supposed to pour some more water into the circulating system. So that is the temperature. For temperature measurement, the property, the physical expansion of the physical expansion of the matter is made use of. There is another version. Instead of this vapor pressure thermometer, there is also liquid pressure thermometer. There is only liquid is made use of. That is what are the volatile and non-liquid, some chemical name, you can refer the standard textbooks. And the liquid pressure thermometer, the whole volume is made up of only one liquid, probably mercury. Mercury also can be used. The bulb and this tubing, the Bourdon gauge, everything is made up of is filled up with the liquid. Now if when it is immersed, then the liquid try to expand, but it's not allowed to expand because it's a constant volume. So you find this to the extent of expansion of then compression is there, and then it develops pressure. Since it's a constant volume, since there is no gap of expansion, that much expansion results in a high pressure of the liquid. That pressure is right in the Bourdon gauge again. But the problem in such a liquid pressure thermometer is any intermediate temperature. So this may be T1, and here if you have T2 and T3, and all these temperature will contribute towards the pressure of the liquid. So whereas in vapor pressure thermometer and free surface of volatile liquid alone, the temperature of the free surface of volatile liquid alone decides the pressure of the vapor. Any other temperature in between will, because the vapor is little compressible, it will not affect the vapor pressure. Any intermediate temperature will not affect the vapor pressure. Hence we find the vapor pressure thermometer is more accurate than liquid pressure thermometer. Hence this vapor thermometer is often used. A liquid pressure thermometer, if you are using, then the compensation, we should take another tubing, and this much expansion is given in the opposite direction, so that any error is compensated and it is given. So it is little elaborate in construction and more costly. Yeah. So that is regarding the dimensional change of matter by temperature variations. That is what we made use of. Now next we have the electrical property, that is thermo EMF. Thermo EMF. First we take thermo EMF. That is electromotive. EMF is electromotive force. Electromotive force. Electromotive force, EMF. That is, we have two wires of homogeneous material, wire A and wire B, or matter A or element A and element B, and they are joined together. It's a homogeneous material, made up of homogeneous material, two wires, and the two junctions, it's a junction. It is a junction where the two ends of the material are connected together. Junction, this is one junction, this other junction, by welding or soldering. They are they're better. I mean, or just have strong twisting, so that you find there is sufficient electrical contact. That is what is important. You can get it by simple twisting or soldering or welding. So the two junctions, when they are at two different temperatures, T1 and T2, then what happens? An EMF is developed in the circuit made up of these two wires, wire A and B, and that is called Seebeck effect. That is called Seebeck effect. The two thermocouple wires, such material having this property of developing EMF, when the junctions are subjected to different temperatures, such materials are called thermocouple materials. And when two thermocouple material junctions are at different temperatures, an electromotive force is developed in this circuit. That is our Seebeck effect. And later on, this was found out nearly in the 19th century, early part of 19th century, and later on Peltier and Thomson also found out some more effect, thermal effect on this thermocouple wire. That is Peltier effect is when the current flows in the thermocouple circuit. So current is flowing like this, say I, current I flows. Once they are in two different temperatures, EMF developed, that EMF divided by the total resistance of the wire gives rise to current flow in the circuit. Due to current flow, heat is absorbed in the hot junction. Of course, T1 and T2, so suppose T1 is greater than T2. Then we say T1 is the hot junction and T2 is the cold junction. So when the due to current flow in the thermocouple wire, the heat is absorbed at the hot junction and heat is liberated at the cold junction. What is the effect? See, it is amounting to more or less a loading effect in the instrumentation. So now the T1 is due to this current flow is reduced from T1 to say some other T1 dash, because heat is removed due to current flow, so it is reduced. So finally we are measuring the reduced temperature. It is exactly the loading effect. So that is Peltier effect. Then one more effect by Thomson effect. That is when the current flow and the heat flow. Now heat flows always from higher temperature to lower temperature. So like this, heat flows like this. Now you find in one wire the heat flow and current flow are in the same direction, that is in the wire B. In the wire A, the current flow and heat flow are opposite in directions. So if we find when the current flow and heat flow are in same direction, heat is liberated to the atmosphere. That is the Thomson effect. Heat is liberated, and in the wire where the current flow and the heat flow are opposite, heat is absorbed from the atmosphere by the wire. So that is the Thomson effect. So these are the three effects that are happening in a thermocouple circuit, in a thermocouple circuit. Though there are but in practice we are using some 4 laws in actual measurement of temperature by using thermocouple. Those 4 laws are explained here. What are the 4 laws? That is empirical laws used in actual measurement of temperature by using thermocouples, and they have to be understood if at all we are going to make use of thermocouple. The first one is the intermediate temperature. We are talking about so far we are talking about the junction temperatures, and the voltage developed in such a thermal EMF or voltage developed in such a thermocouple wire is depending only on T1 and T2. That is being made more elaborate. Even when the intermediate temperature happens to be T3 or T3, T4, T5, T6, something like that, you find the voltage developed in the first circuit is same as the voltage developed in the second thermocouple circuit. That means intermediate temperatures of these 2 wires will not affect the EMF developed due to the temperature difference of T1 and T2 in the 2 junctions. Intermediate temperature can be anything. So that is the first law of thermocouples. Second law states we can bring a third element, because thermocouple circuit is made up of 2 elements, homogeneous element A and B. Now I am bringing a third element C, cutting the material A at these 2 points and connecting the third member C. Now here the voltage developed will not be affected if, that is important, if the 2 new junctions are at the same temperature. Now 2 new junctions are at T3, and earlier main junction temperatures are T1 and T2. But when you are bringing third material and these 2 junctions we are going to connect with the material A should be at the same temperature. This is the property what is made use of in the voltage measurement of the thermocouple circuit. When you want to measure thermocouple circuit, what you are doing? We insert a voltmeter. Voltmeter mostly consists of copper wire, and we find the 2 junctions we are making is at the temperature of the atmospheric condition. Atmospheric temperature is the new junction temperatures, so same temperature. So this condition is satisfied. Hence you find the voltage developed, thermal EMF developed in such circuits is no way affected in the earlier circuit where there is no such voltmeter. Also we find that the law of intermediate temperature also holds good. The third material can be exposed to any temperature later, like this say T4, it will not affect the EMF. And here we find the third material is connected at one of the 2 junctions. Here at the T1 junction, the new material is connected. That is, this is what is made use of in the measurement of temperature, cutting tool temperature in a lathe. See, the lathe headstock and the tailstock is here, and the material is turned in between these two headstock and tailstock. This tailstock is a movable one, and this is headstock which is being rotated. And when we have the cutting tool somewhat like this, if see, this is the hot junction. This temperature is made, is to be measured, and normally this high-speed steel material, the cutting tool is made of high-speed steel. The material may be mild steel. So two different materials. So it is analogous to two different elements, and the junction is cutting point is junction. Then away from the cutting point, we take another slip ring. Somewhat like slip ring arrangement, and we have the brush contact, and with a spring loading, and this also we take one point from there. Between these two we connect a voltmeter, and is analogous to this one. This T1 is the temperature, that is, this is at atmospheric temperature, this is also atmospheric temperature away from the cutting tool. Between these two new junctions, we are connecting a voltmeter by suitable mechanism. That's all. Slip ring and the brush is a new mechanism. That means at the temperature, at the atmospheric temperature, we connect the voltmeter. That is, T1 is split and made to connect a voltmeter. That is this is circuit what is made use of in the temperature measurement of cutting tool in a lathe, for example. So that is our third one, second one. The third law states the calibration of the thermocouple elements, and we have got a number of elements exhibiting this thermocouple thermo EMF property, and then suppose 10 elements means, then permutation combination, you may get a number of combinations with the 10 elements, hundreds of combinations with these 10 various elements. And calibrating each pair is a very laborious and time consuming job. So what is done normally is each material is calibrated with platinum. With the platinum, normally platinum as one material, all other materials are platinum is one material, all other material each time is taken with the platinum, one thermocouple is made, and that calibration, what is EMF developed under different temperatures, one temperature, cold junction temperature being 0 degree centigrade, ice point. With the cold junction temperature as ice point, all elements are calibrated with the platinum. That chart is already available. And if we want to combine any two elements, then from this calibrated chart we can easily obtain the characteristic without doing actually the full calibration. That is what is explained as the third law. The first you find the thermocouple is made up of material A and C, and the voltage EMF developed is EAC, if you call. Similarly, if you have got material C and material B with the same temperature, T1, T2, hot junction, cold junction temperature, and if you call the thermal EMF as EBC, the C material is common in both, that is the same as platinum. Platinum is the common material. Then if you have a pair between A and B, thermocouple pair, that EMF developed for that same T1 and T2 is obtained. EAB is given either addition of these two voltages or the difference between these two voltages, what is written here. And whether plus or minus, how to locate it, how to fix that plus or minus, at least one temperature, that is having this T2 as 0 temperature, 0 degree centigrade, you have to have one temperature, any known temperature T1, and find that voltage. For that two temperature differences, whether by adding you get this voltage or by the difference between this you get the voltage, you can check. Once you check for one reading, later you need not do the calibration, simply obtain this calibration curve from other points for calibration curve from these two standard charts. So that is the calibration procedure is made simple by the third law. The fourth law states the cold junction temperature need not be always 0 degree centigrade, it can be any other temperature. Preferably the atmospheric temperature. So that is explained like this. Suppose we have the thermocouple pair A and B. First the EMF developed between T1 and T2. T1 is these two temperatures of the junctions T1 and T2. T1 is larger than T2. If you call that voltage developed is E T1 T2, and then same pair when it measures between T2 and T3, the same thermocouple pair. If you call it E T2 and T3, then voltage developed between T1 and T3 will be equal to, that is E T1 T3, that is here T1, this is T3, this junction, same pair, thermocouple pair, that is E T1 T3 is equal to E T1 T2 plus E T2 T3. That is, mostly you will find your T2 is our atmospheric temperature. So we measure having atmospheric temperature as the cold junction, and then the T3 is the higher temperature. That voltage we measure it, and from the chart for the A and B material combination, you can get from T1 to T2 what is the voltage. Add these two voltages, then you know the total EMF developed for a temperature difference of T1 and T3. So corresponding to the temperature, what is the temperature T3, you can find out. That is how the fourth law is made use of. That is, the cold junction temperature is not always 0 degrees centigrade, it can be any other temperature. These are the 4 laws normally used in actual practice, and you find even though there are many materials exhibiting the thermocouple property, in actual practice we find some 5 pairs are alone, 5 pairs, 1, 2, 3, 4, 5 pairs. These are the 5 thermocouple pairs are often used in measurement. First one is platinum and platinum rhodium. Wire A may be platinum, wire B is platinum rhodium alloy. This I have given percentage, this is 10% of rhodium, 90% platinum, 10% rhodium, then it is called platinum rhodium alloy. Such a percentage is made use of 0 to 1500 degrees centigrade, and it is more accurate than the other pair. We find 0.25% of the reading, and it is least sensitive among the available thermocouple pair. This is least sensitive. That means for platinum rhodium for 1500 at 1500 degrees centigrade, it develops a voltage of say about 15 millivolts. That is what it develops. From 0 to 1500, 0 degree is cold junction temperature, 1500 degree is the hot junction temperature, then it develops around 15 millivolt. Whereas we find the copper constantum, chromal alumal constantum, copper constantum, chromal alumal, it develops around chromal alumal 1000 degrees 50 at 1000 for 1000 degree for 1000 degrees centigrade, it develops for 1000 degrees centigrade difference, it develops around 50 millivolt. So and the other one chromal constantum for at 500 degrees centigrade, at chromal constantum at 500 degrees centigrade, chromal constantum 50 millivolts. So it is more sensitive, it's more sensitive. Chromal constantum, iron constantum develops around 750 at 750 degrees centigrade as 50 millivolt. So we find from these characteristics the copper constantum is it has got measurement range of around 350, up to 350 alone it is made use of, and it develops at that temperature around 15 millivolt. So these are some of the values for this important thermocouple pair, and in this you find the least sensitivity we have got platinum rhodium, but it is having very high accuracy, higher accuracy than the other pair. It is because it is inert in any even in oxidizing atmosphere, the platinum is the most inert material, it does not get contaminated. Whereas you find the copper constantum can be used only up to 300 degrees centigrade, 300 or 350, that is this range. Beyond that, the copper gets oxidized. So we cannot, that then the calibration is lost. It is supposed to be pure and homogeneous material. So when it is contaminated beyond 300 degree or 350 degree centigrade, then you cannot make use of it. So it is very least range. And the another important point is at higher temperatures, say around 1000 degrees centigrade and all, or around 1000 degrees centigrade, if there is inert atmosphere, I mean if there is some oxidizing atmosphere, the wire, thermocouple wire absorbs the nearby materials. Normally we find the thermocouple wire is put in a production tube, somewhat like this, and here we have the thermocouple wire. Thermocouple wire is taken like this. We have got a cover and then it is taken. So it is called production tube, made up of iron. So it is to protect the junction, otherwise you will find some flue gas flowing. If you want to find the flue gas temperature, some dust and all may contaminate, may fall on the wire, and it may get contaminated, and it may change the calibration curve. So for that, such things are so it is in the pipeline. So it is just inserted in pipeline, and there is production tube. And at say 1000 degree and all, then you find this material absorbs some of the material nearby in the vicinity. If you have got any metal, it also absorbs. So beyond 1000 degree centigrade, we have to be careful that the wire doesn't get contaminated, or when it absorbs such material, foreign material, that the calibration gets changed. So that is how the in actual usage of thermocouple you have to take care. We have seen that in thermocouple the output voltage in a single thermocouple is in terms of millivolt, and it is common practice to increase sensitivity. A number of such thermocouples are joined together in series, and then they are used as thermopile. That is what is called thermopile. It contains more than one pair of thermocouple elements. Here you have got two such pairs, and this is a hot junction. The cold junction is say atmospheric temperature. So you have got two such junctions. So the net voltage, net EMF output is twice the output for a single thermo. So this is wire A, this is wire B, this is wire A, wire B. So two pairs are used. This is hot junction. They will be very near. It's only for clarity's sake I have drawn apart, but otherwise you will find these two things very near, and they are put in over a surface, and between temperature between the atmospheric temperature and this, you will have the difference. Voltage is developed, and that voltage will come. That is twice the voltage of the single thermocouple element. But here I have shown only two. You can have 3, 4, or 5, or 6. Any such pairs can be connected in series in the same way, and you will find 6 means 6 times the voltage of the single pair. So these are available, and they are called thermopile. It is only number of thermocouple elements put together. Naturally, the thermocouple wire can be used only when the temperature of measurement is lower than the the melting point of the one of the thermocouple wires, lower melting point of the. We have got two elements. One element will have a lower thermal lower melting point. So the measurement temperature should be less than that element. That is the limitation. Suppose the temperature is high, that one of the thermocouple wire may be melting under that temperature. Then you can adopt any one of these two following techniques. So measurement of higher temperatures higher than the melting point of one of the wires can be measured by adopting these two techniques. Any one of these two techniques, that is called continuous cooling method. The other one is called pulse cooling method. These are the two methods available. And first, the continuous cooling method. We have a pipeline carrying the water, which is a part of its passage is exposed to the hot gas coming. This hot gas temperature Tg is very large. It may melt the thermocouple wire. So what is done is thermocouple wire is made use of to measure the inlet water temperature. Water is coming here, inlet water temperature at this point just before entry, and later on the hot gas transmits the heat to the water in this area, cylindrical area of say area A. Area A is the cylindrical area through which heat is flowing into water. So water gets heated up and the coming out water from this section will be having a higher temperature. So these two temperatures, inlet temperature before this heating zone and outlet temperature from the heating zone are measured by using the thermocouple wire, that is T1 and T2, which is very low value. So this is what is measured. From this measured temperatures you can compute the hot gas temperature. Once you know the heat conducted through this area A is equal to heat taken by the water in this particular in a flow particular second. This is per second. So you find this mass flow rate of water per second, and Cp is the ratio of the specific heat of water, and T2 is the high temperature of the water and the incoming temperature of water, and A is the circular area through which the heat is conducted. H is heat transfer coefficient. Heat transfer coefficient is having watt per, that is joule per second. Joule per second, that is watt per meter square per degree centigrade. Yeah, per degree centigrade per second. It's per second. So that's why this is kilogram per second, and here also per second unit is there. And Tg is the gas temperature, T2 is the output temperature of water. So that heat is conducted between temperature difference of Tg and T2. So that is heat conduction is equal to heat gained by the water, flowing water. They are equated. From this you can measure M is known by measurement, and T1 and T2 are measured by having the thermocouple, and A and H and all constants available. So we know the unknown temperature Tg. This is the continuous cooling method. In we have got another method called pulse cooling method. In this you have a pipeline carrying the cold air, and the hot air just in a pipeline it is thermocouple is situated. So normally the cold air is allowed through by the wall, and cold air is at a higher pressure it will be flowing from the inner pipe to the main pipe. So that you will find the thermocouple junction is always at the smaller temperature, that is this is the temperature, smaller temperature Tc1 for example. It is much less than the hot gas temperature. Suppose you want to measure the hot gas temperature, what do you do? Close the valve. Immediately this hot gas will enter into this pipe, support pipe, and the junction temperature will start rising. We know this is a first order instrument, any temperature measuring instrument, first order instruments. So they follow this equation, differential equation. Tau is the time constant of the thermocouple element, the rate of rise of the temperature plus the temperature thermal that the junction temperature is equal to Tg. This is the first order that is tau d plus 1 xo is equal to k times xa. This is standard format. And here if you substitute for Tc is E by K, you can also instead of Tc you can write E, and this also you can write E, because the voltage thermo EMF is proportional to Tc, and here you can write KTG. So you find it is a typical the typical first order instrument. So the temperature starts increasing exponentially. We know the equation is exponentially. Output voltage is given exponential, is an exponential function. So it start increasing, but before it reaches this gas temperature at which one of the wire may melt, you again allow the cold air, and here at point 1 cold air is cut, is removed, cooling is off, cold air is cut, and start rising. Before reaches melting point, we again open the cold air, so now cooling is on, then later it starts reducing temperature. But from these characteristics we can gauge, we can get this according using this equation we can find out the hot gas temperature. That is, we realize this equation, mathematical equation in this circuit, that is E is proportional to Tc or E, dE by dt. For E we have got output voltage, and through a differentiator we get the E dash. That is multiplied by the tau, so proportional to the time constant of the circuit of the thermocouple element, multiply these two things, and the tau E dot plus the same E is taken, this adder. By adding these two quantities you will get EO, that is tau E dot plus E, that is the plus E, that gives the proportionate quantity for the Tg. EO is proportional to Tg because K into Tg. So by having some known temperature you can find this EO can be calibrated, and later on you can use it for unknown temperature. So that is how the pulse cooling method is made use of to measure even higher temperature, higher than the melting point of one of the wires.